So for the last 3-4 weeks of the course, whatever it is, we're going to leave physical chemistry behind. We're going to leave our calculators behind, and we're going to start looking at types of reactions, focusing on organic reactions, some fundamental types of organic reactions that those of you who've done A-level, you might remember those from A-level. Those of you who haven't done A-level, doesn't matter, because we're going to do the entire A-level organic reaction curriculum in 3 weeks. So anyway, there's very important types of reactions that you do need to learn to identify, not so much to give them cute names, but so that you recognize the mechanisms associated with them. And so we'll talk about the 5 big types of organic reaction that we're going to encounter. And then we'll also, at the end of this particular movie or set of movies, talk about some important types of reactants with which you might not be very familiar. So anyway, the first type of organic reaction we'll mention, acid-base reactions, straightforward proton exchange that we're world experts in. For example, here is an organic acid, a carboxylic acid with that acidic proton there. Here is an organic base, the amine, that has that lone pair of electrons there. Proton goes from the acid to the base, leaving behind the conjugate base of the acid and the conjugate acid of the base. We're not going to see a large number of acid-base reactions, but those we do see will be rather significant. Another type of reaction, I'm sure after the last week will make you so excited and enthusiastic, are organic redox reactions. Now, while the fundamental idea of redox, right, reduction, gaining electrons, oxidation, losing electrons are there, organic chemists regard redox reactions from a rather different perspective, as I'll try to illustrate here. So here is an alcohol which can be oxidized to an aldehyde. Okay, now you might not look at that and say, how on earth is this an oxidation? Well, the formula of the alcohol, C3H8O, the formula of the aldehyde, C3H6O. An organic chemist would look at this and say, we have lost hydrogen atoms. Losing hydrogen atoms is one indication of an oxidation, in the same way that gaining electrons would be an indication of a reduction. Gaining hydrogen atoms would be an indication of a reduction. We can demonstrate to ourselves that this is indeed an oxidation by applying oxidation numbers. The oxygens -2, hydrogens are +1, so that's +8. +8 -2 leaves -6 to be taken care of by the 3 carbons, so the carbon's -2. Over here, you've got the oxygen -2, only 6 hydrogens at +1, so that leaves a total of +4 to be handled by the 3 carbons, so the carbon is -4/3. So the oxidation number, the average oxidation number of the carbon has increased, thus it is indeed an oxidation. Now, the way that organic chemists would describe this oxidation is they're not going to do anything fancy like talk about necessarily what reagents you're going to use, although of course they will talk about that when they get specific, but they will use a little indication, O in square brackets, to indicate this is an oxidation. Now we can do another oxidation with an aldehyde, making our carboxylic acid. So I'm going to ask you to pause and demonstrate to yourselves that this is indeed an oxidation. Back from pause. Well, first of all, the formula of this is C3H6O2. So an organic chemist would go no further than just pointing out we have gained an oxygen. When you gain an oxygen atom, that can be an indication of an oxidation, in the same way that if you lose an oxygen atom, that can be an indication of a reduction. Okay, and so what happens to oxygen atoms, what happens to hydrogen atoms, definitely something we're going to be looking at as we look at organic redox. You can, of course, demonstrate to yourselves that it is indeed an oxidation by looking at the numbers, the average oxidation number of the carbon. Oxygen, 2 of those, that's -4. Hydrogens here, +6, so +6 -4 leaves another -2 to be taken care of by the 3 carbons. In other words, each carbon is -2/3. Now I do want to remind you, and I hope you have gone back and looked at the fundamental organic stuff we did last term, that there's several ways to depict organic compounds. This way here, yes, you can kind of see what's going on. In fact, it's really emphasized for you in terms of the oxygens, but don't forget you can also draw it out like this so that you can see what's happening to the hydrogens as well. So we lose a hydrogen from that carbon, we lose a hydrogen from the oxygen as we do that first oxidation, and then of course you can see here that we got the effectively the hydrogen from there we can think of pops onto the second oxygen. Now, we're used to seeing a redox in that you have a oxidizing agent and a reducing agent together, and both are just as important. For organic chemists, it's always the organic-y thing that's the important. Whatever we're having to add in here as the oxidizing agent to make this oxidation happen, not as important as the fact that alcohols are going to an aldehyde. So in the same way that we will depict just an oxidation as being O in these square brackets, knowing this implies an oxidizing agent, we can look at the reverse reaction from the aldehyde back to the alcohol, gaining 2 hydrogen atoms, thus that is a reduction, going down in oxidation number, that is a reduction, by using the abbreviation H in little square brackets. You see O in square brackets, it means oxidizing agent, H in square brackets means reducing agent required here. So I can just add that reverse arrow in there for all of the other ones. So I talked quite a lot about the redox there. We'll actually do that redox reactions in the last week of term, and hopefully the different perspective that organic chemists use will not be overly confusing compared to what we did last week.